We now look at chapter 5, which is eigenvalues and eigenvectors. So in this section, we will learn what are eigenvalues and what are eigenvectors. So and why do we need them? So what are we trying to find there? Basically, what the question is that if we have an n by n matrix, like a square matrix, then are there any non-zero vectors in the matrix such that a times x, so a vector a times x is equal to a scalar multiple of the vector itself. So something like we use the letter lambda here for scalar, but if you cannot write it or you don't understand it, you can always write like r or k. Okay. So that is kind of strange, like matrix is being replaced by a number. That's what we want to see. So, so this scalar value, if a vector behaves in that way, the scalar is called the eigenvalue of that vector, and the vector itself is called the eigenvector. So we will learn how to find them, and also we can check whether a given vector is an eigenvector of a matrix or not, or a given value scalar is an eigenvalue of the matrix or not. Okay. Oops. So here we are going to start by looking at this example 1. Let A be this matrix, and u and v vectors are given, and the question is, are u and v eigenvectors of the matrix A? So eigenvector, as I just mentioned, is a vector which behaves in this way, or which satisfies this equation, that when you multiply the vector with the matrix A like that, A times x, you get x but with a scalar outside. So lambda, we call it lambda. Okay. Now, as I said, lambda is going to be called the eigenvalue, and the vector is going to be called eigenvector. Now, if x is an eigenvector, remember this, if x is an eigenvector of a matrix A, then, and the corresponding eigenvalue is lambda, then every non-zero scalar multiple of x is also an eigenvector of A. So this is kind of a small theorem, and here is kind of the proof that AU means if the AX is equal to lambda x. This we know, right? So now let's say we have another vector u, which is c times x, and that means u vector is a scalar multiple of the vector x. Then this u is also going to be an eigenvector of A. How? Because remember, the eigenvector has to satisfy the condition this. So if I start by multiplying u with A, so I get AU is equal to, now I replace the value of u, cx. So ACX is equal to, now we can move around the scalar but not the vectors. So I put the c in front, and then I have A times x. So c scalar multiplied by A times x, which is a vector. But A times x is lambda x. So what will now happen? C is a scalar, lambda is a scalar, and then we have a vector. Then by properties of the vectors, the two scalars can be combined, put together, so it becomes lambda times c and then x. So we end up getting C. So C, put C back with the x, it becomes a u vector. So we are getting back our A times U, lambda times U. So which means lambda, the eigenvalue lambda has another any scalar multiple of x vector is going to be an eigenvector of the same value. Also, if you have two eigenvectors corresponding to the same eigenvalue, then their sum is also an eigenvalue of the eigenvector of the matrix corresponding to the same eigenvalue. And this is something you may prove. So how will you prove it? You will say let u equal, first thing is let x and y be two vectors, eigenvectors of lambda, xx and y be eigenvectors of lambda. So what does that mean? It means a times x is equal to lambda x and a times y is equal to lambda y. And now you want to check what happens when I do a times x plus y. So I will leave it here. You can finish the proof. Okay. What are eigenspaces? If A is an n by n matrix with an eigenvalue lambda, the set of all eigenvectors of lambda together with the zero vector is a subspace of R. And this subspace is called the eigenspace of lambda. The eigenvectors of A corresponding to lambda are the non-zero solutions of this equation. So this is some calculations that we have to do when we are finding the eigenvalues and eigenvectors. Okay, so here is a second example. I am going to do all the example again. Let A be this matrix, and given that 1 and 2 are eigenvalues of A, find a basis for the corresponding eigenspaces. Okay, there are some theorems which might be helpful when we are solving the problem. So theorem 1 is the eigenvalues of a triangular matrix are the entries on its main diagonal. Now remember, 0 can be an eigenvalue of some matrix. Okay. Second theorem is if V1 up to Vr are eigenvectors that correspond to distinct eigenvalues, lambda 1, lambda 2 up to lambda r of an n by n matrix, then these all V1 V up to Vr, they form a linearly independent set. So if you all the vectors eigenvectors combined of a matrix, though if you make a set out of those eigenvectors, then that set will be linearly independent. So first example, so remember we were given a matrix A and we were given two vectors and we had to check whether these are eigenvectors of A or not. So what I did here, I just multiplied one by one the vectors with the matrix. So I did A times U. Okay, did the calculation and I got 0, 0, 0. Okay. So what does that mean? It means we are getting Ax is equal to 0. So if either we can say this is not an eigenvector, or we can say that the only eigenvector of this matrix is 0, 0, 0. But is that allowed? No, this is not an eigenvector. Why? Because remember in the beginning we said a non-zero. We are trying to find the non-zero solutions. Here, remember here? non-zero vector. So lambda may be 0, but x, the eigenvector, cannot be 0. So this is not an eigenvector, but when I do a v, I got 1 0 0, and that's what my v was. So I can say it is a v is equal to 1 times v. So eigenvalue, it means it's 1. So lambda is 1, and the eigenvector, you can call it by any name. V in this case is the vector 1 0 0. So this is the eigenvector of the matrix and corresponding to the lambda equal to 1. Second example, so we have to check whether these are eigenvalues of A or not. So what we do, find a base. Okay, then we have to find a basis for the corresponding eigenspace. So remember, we just learned in those theorems that all the eigenvectors will be linearly independent, and they will form a this eigenspace of the lambda, whatever value lambda has, and that eigenspace is a subspace of Rm. So the question is asking us to find example 2 here. Find a basis for the corresponding. Okay, so what it means is that we actually have to find the eigenvectors. When it says find a basis for the eigenspace, so we just learned that the eigenspace will have the eigenvectors will be the basis of the eigenspace. So we have to find the eigenvectors for related to each of these given eigenvalues. So how do we do that? This is how we do that. So we first form or compute the matrix A minus lambda I, because remember it said up there that the equation A minus lambda I times x is equal to 0. This is the equation that the eigenvector must satisfy, a non-zero eigenvector. So this is what I am doing. I took the matrix and I am going to subtract lambda times I. Now what I will be of the same size as A, but its entries are being multiplied by lambda. Now what are the entries of an identity matrix? On a remember, it has most of the entries are 0, just entries on the diagonal which are all 1, and then when we multiply by lambda we get a diagonal matrix, or a matrix which has lambda on at each diagonal value. So then I combine, compute the A minus lambda I, and I get this triangle, this matrix. Now what I am going to do is use this matrix for each eigenvalue one by one, and then figure out what our eigenvector will look like. So when lambda is equal to 1, so remember lambda has two given values, 1 and 2. So when lambda is 1, we say let the eigenvector be, you can just pick any vector, a, b, x, p, u, v, w, whatever, x, y. And remember, if you write it as a column vector, that's so fine, but if you write it horizontally as a row vector, make sure to put a t on top. That means the transpose. So the eigenvector must be column vector. So what do? I am trying to look for the solutions of this equation. So my matrix here is A minus lambda I, and then I have to find the solution of this homogeneous equation, which means I can set it with augment the matrix with the 0 0 0 vector. But even if I don't, I just work with the matrix or perform the row operations on the matrix, and still I will be able to figure out the values of the individual components of the vector. Okay. So when I plug in lambda, so in first case the lambda is 1. So when I plug in 1 in the matrix A minus lambda I, this one, so what happens, I am getting this matrix. Because it becomes A minus I, so it is, so first row, if you notice, is row of zeros, and remember we want the row of zeros at the end, so we have to swap this row with some, so better swap it with the last row, because last row has a 1 in the first position, which can be our pivot, and also we want the zeros in the end. So I did that and then performed other row operations, and I end up getting finally this matrix, which is in row echelon, reduced echelon form. Now I try to see what are my free variables here. So if you note, there is no pivot in the second column and there is no pivot in the fourth column. So which means that x2 and x4 are free variables. So you can, since I took the u vector, so u2 and u4 are free variables. And now I should try to write the others in terms of u2 or u4. Or mixture of u2 and u4. So I am getting, so because it's in the reduced echelon form, so it's easy. So the first row gives me u1 plus 2 u4 equal to 0. This is the equation I get from this first row, which gives me u2 is equal to, well, u1 is equal to 2x negative 2x4. Then from the second row, I get u3 minus 2x4 is equal to 0, which will give me u3 is equal to 2x4. So if you want, you can let the one of the free variable be called s and the other free variable will be called t, and then go use those in writing the equations or finding the basis. But even if you use u2 and u4 or x2 or and x4, that's fine. Okay, I am calling them s and t. So my u2 free variable, I am calling it s, and the u4 free variable, I am calling it t. So I can now write u1 as negative 2t, u2 will be equal to s because that's what we set it for, and then u3 we found is 2x4, so it means 2t, and then x4 is just t. So I put all of them in place here, and then I can pull out the separate the vectors and pull out the s and the t. So I hope you know how to get from here to here. If not, then please ask question when in class. Okay, so now these are our eigenvectors. So these two are the eigenvectors associated with lambda. Okay, so the eigenvectors associated with the eigenvalue lambda is equal to 1 are these two, 0, 1, 0, 0 and the negative 2, 0, 2, 1. And these vectors form a basis for the eigenspace of lambda. Now, for